Welcome back to statistics. In this video, we're going to dive a little deeper into the notion of the sampling distribution of xBar. Actually, we're going to do that in the next several videos because there's several aspects of the sampling distribution that we need to be aware of. Here, we're going to be mostly concerned with the shape of the sampling distribution. But in subsequent videos, we'll also look at the center of the sampling distribution as measured by the mean, and the spread of the sampling distribution as measured by the standard deviation. All three of these aspects, shape, center, and spread, are important for the work we're going to be doing in inferential statistics. So let's begin with the notion of the shape. For the shape of the sampling distribution of xBar, there are really two main facts that we need to be aware of. The first is that the sampling distribution of xBar has a shape that is more normal than the shape of the population distribution. So even if the population distribution has a shape that's very non-normal, like bimodal or something, the sampling distribution of xBar will tend to have a shape that's more normal in character. The second fact is that as the sample size gets larger, the shape of the sampling distribution becomes ever more normal. So as the sample size increases, the sampling distribution shape just tends to become more and more normal in character. So let's take a look at some data that bears this out. I'm going to go over here to SALT, and I've loaded a couple of data sets in that will illustrate these ideas. The first one is a very large set of uniform random numbers distributed between 0 and 1. So let me show you the histogram here. There you see it. There's actually 100,000 individuals in this data set, 100,000 numbers, all uniformly distributed between 0 and 1. These were generated by a computer using what's called a pseudo-random number generator. So this is a computer program that spits out numbers that, for statistical purposes, have all the characteristics of genuinely random numbers. A pseudo-random number generator essentially is an update of the old-fashioned table of random digits, but they can do a lot more. So as you see, all the numbers are distributed between 0 and 1 here, and the bars are all approximately of the same height. And so that's what we mean by a uniform distribution. So what we want to do then is we're going to think of this as our population, these 100,000 numbers as our population. And we're going to take random samples from the population, compute a sample mean, and throw those into a histogram to form the sampling distribution. So let me go over here to the sampling tab and get that started. We'll select our variable. There's only one variable in this data set. I'm going to select a sample size that's pretty small here, about 2. And I'll generate 1,000 samples at a time, and we will build up the sampling distribution as we've done before. So it takes it a minute to compute because there's such a large population. But there's our first 1,000 samples, so 1,000 dots in this graph, each of which represents an xbar value calculated from a sample of size 2 here. That we have. And so let me just do this a few more times so we can build up a few more dots in our picture. So already you see that the sampling distribution of the sample mean, even when the sample size is small, like 2, is not uniform anymore. Here's down here in the lower left, you see the population distribution. This is just the distribution of those 100,000 numbers. It's uniform, but the sampling distribution has a more normal shape. It's not exactly normal, Actually looks more triangular here, but it's more normal than the uniform distribution. Now I want you to watch what happens as I increase the sample size. I'm going to just increase it by a factor of 4 each time. So now I'll do samples of size 8. And let's see what that does. So the graph will get reset. You'll crank and grind for a minute, and we'll get those samples. So there we are. There's our first 1,000. Let me, as usual, turn the crank a few more times and build up the sampling distribution that way. So now you see the sampling distribution. Yet again, it's certainly not a uniform distribution, which was the population distribution. And I would argue that that's a little less triangular and a little more normal looking than when we had a sample size of just 2. So now let me increase the sample size by a factor of 4 again and regenerate the samples. There we go. There's our first 1,000, 2,000, 3,000, and 4,000 samples. And that's beginning to look a whole lot like a normal distribution, a bell-shaped curve. And this process only continues as you go further. And so just for grins, I'll do 128 as our sample size, and you'll see that we have a distribution that is pretty decidedly normal here. So that's an illustration of both those ideas we saw on the slides. That is, the sampling distribution of xBar is more normal than the population, and that trend increases as the sample size gets larger. Let me show you another example of the same basic phenomenon, but this time with a very different population. This is a population consisting of 10,000 weights in ounces of fruits. There were 4 different types of fruits among these 10,000 samples, so that's why you see the clustering of the data here. Each type tends to weigh, similar to its own type, but different than other types. So you see 4 modes. This is a multimodal distribution. Again, let's begin by taking samples from the distribution and looking at the sampling distribution of xBar. So I'll start out in the same way as before with samples of size 2, and I'll generate 1,000 of those at a whack. So here's samples of size 2 from that distribution. Here, because you can see that there's some kind of trace of the population distribution here in the sampling distribution of xBar when the sample size is as low as 2. Again, the distribution of the population of the individual fruit weights here, and the distribution of the sample means, the xBars here. But notice there's actually more than 4 peaks here. I'm counting 1, 2, 3, 4, 5, 6, and there may even be some more down here. It's hard to say at this point that this is becoming normal, but I think you can see it if we increase the sample size. So I'll go to 8 now, and we'll generate. There we have 4,000 xBars in that plot. I think you'd agree that this is certainly beginning to look like a normal distribution with just 8 samples in it. You can still see a left tail in this distribution. And actually, let me color both tails here. That left tail is a relic of the sort of left tail, the left skew of our original distribution. But again, as the sample size increases, that left tail will even out, and we'll get increasingly normal distributions for the sampling distribution. So now I'm looking at samples of size 32, And here you'd be hard pressed to identify a left tail. This is beginning to look very definitely normal. And then one more factor of 4, I'll go up to a sample size of 128. Generate 4,000 here. And that is, that's, for all intents and purposes, that is a normal distribution. So what we've seen here is that no matter what the shape of the population distribution, the sampling distribution of X bar tends to become more normal. And as I said in the introduction to this video, there's some other factors that will come into play as well when we start looking at the center and the spread. But this basic fact about the sampling distribution of X bar is a little bit surprising. You wouldn't expect just going in that sampling distributions of X bar would tend to become normal, especially as the sample size increases. But it is a fact. And we'll be exploring this fact and others further in our next couple of videos. So I hope you found this helpful, and we'll catch you next time. Y'all take care.